Hello there, Mr. Sutton bringing you this lesson on antiderivatives, part 2. In this one, we're going to be finding general antiderivatives of functions that can be simplified first, and also antiderivatives of simple compositions of functions. For your warm-up, pause the video and try to take this antiderivative. Now I know what you're thinking, Mr. Sutton, that wasn't fair. You never taught us how to take the antiderivative of a product. Well, at some point you learned the derivative of a product, right? But before you even knew that, there was a way to do this kind of problem using just the power rule. So by the same token, doing antiderivatives, there is a way to do this problem using just the reverse power rule. Just like when you were dealing with derivatives, this problem will be a lot easier to take the antiderivative if you simplify before trying to do it. So expand the 3x minus 5. That'll be 9x squared minus 30x plus 25. And then we can distribute that 4x. That'll be 36x cubed minus 120x squared plus 100x. This is something we can take the antiderivative of term by term. So let's go ahead and do that. So first term, bump that up to a 4, divide by 4. We've got 9x to the 4th. Next term, this will be an x to the 3rd, divide by 3, we've got negative 40x to the 3rd. And finally, this will become x squared, dividing it by 2, we have 50x squared. And then don't forget the plus c. That is still around. Here's another example that at first glance looks pretty awful. Pause the video and see if you can figure out how to do this one without knowing any new special rules. Let's see what we came up with. So whenever you have a fraction, there's at least a possibility that you can cancel out some common factors. However, we won't know what those are until we actually factor this. So the top, we need things that multiply to negative 54, add up to negative 3. So that'll be x plus 6 and x minus 9. In the bottom, we can factor out an x, leaving x plus 6 inside. X plus 6's cancel. And we can get even more sneaky here. These are really both being divided by the x in the denominator. So x over x would be 1, and we'll have minus 9 over x. Going term by term now, we can now take the antiderivative. So this 1 just becomes an x if you take its antiderivative, and then minus 9 over x, that's going to be minus 9 ln of x. And don't forget the absolute value, and don't forget the plus c. Give this next example a look and see if you can figure out what to do here. Now this looks like a pretty hopeless situation. I mean, the only thing that could bail us out here is if we're taking the square root of a perfect square. Oh, wait a second. Two things that multiply to 64 and add up to 16. Positive 8, positive 8. This is really x plus 8 squared inside. Man, we are so lucky. Well, the square root of a square is just whatever was being squared. So this is really just 1 over x plus 8. And now we just need the antiderivative of this. Now, I think we can agree if this was just 1 over x, our antiderivative would be ln of the absolute value of x plus c. Can we do the same sort of thing with this plus 8 in there? Well, there's only one way to find out. How about we just try it out and then take the derivative and see if we actually get what's inside here. So I want to write this as ln of x plus 8 plus c. What's the derivative of ln of x plus 8? Well, it's 1 over x plus 8. Now you might say, but wait a sec, we've got kind of a function going on inside here. Okay, so we use the chain rule. What's the derivative of x plus 8? Oh, it's a 1, which when we multiply this just gives us 1 over x plus 8. So this actually does work. Awesome. We're going to try some trigonometric antiderivative examples now. See what you can do with this first one. All right, so hopefully you remember about reciprocals and trig functions. We're not really sure what to do when we have a sine squared downstairs, but we know that we can turn that into a cosecant squared in the numerator. And then, what is the antiderivative of cosecant squared of x? Oh, well, it's negative cotan of x. But if you've already got a negative 4 outside here, that's going to end up being positive 4, cotan of x plus c. For this next one, what could we do here? Well, the only thing I can think of to do is maybe split up this fraction so you have 7 over cosine times sine over cosine. If we write it like this, then using, again, reciprocals, trig reciprocals, we can express these as different trig functions. For example, this could be expressed as 7 secant of x, and what's sine over cosine? Oh yeah, that's tangent of x. But wait a sec, we know that secant tan is really the derivative of secant. So this is really just 7 secant of x plus c. For our last slide, we're going to take a look at some antiderivatives involving simple compositions of functions. And by simple, I mean the inner function is a linear function. So let's take a look at our first example, antiderivative of e to the negative 8x. So for this one, we know that e is its own antiderivative and derivative. If you're taking the derivative of e to the negative 8x, if we were taking the derivative of that, that would cause you to write e to the negative 8x, and then you'd have to multiply by, using the chain rule, by a tail of negative 8. So if we want something whose derivative is this, without the negative 8 out in front, that means we're going to have to divide by the negative 8 preemptively. So our antiderivative then would have to be negative 1/8 e to the negative 8x plus c. And let's just double check our work here. So taking the derivative just to check, we're going to have negative 1/8 e to the negative 8x, but then again multiplying by negative 8 as part of our chain rule, that's going to cancel out this coefficient and give us what we had inside here. So in general, whenever you're, let's say that you're taking the antiderivative of a function, and we will note that as big F. Big F is the antiderivative of whatever the f function is. If the function you're taking the antiderivative of has a linear function inside of it, then you can do that by just normally taking the antiderivative of whatever that function is, so big F of whatever was inside of there, but also dividing by the coefficient of that linear term. So let's do a few more examples to flesh this one out. See if you can take this and apply it to these next two examples. All right, so applying it to the second one here, antiderivative of cosine is normally going to be sine. So this would normally be 5 sine of whatever was inside there, but we're going to have to divide by the slope, divide by the tail here. So that's actually going to end up being, let's see, what's 5 divided by 1/8? Oh, 40. So this will end up being 40 sine of 1/8 x plus c. Let's do the same thing over here. Derivative of 1 over something would normally be ln of the something in absolute value, but our something has a linear function with a slope of 3, a derivative of 3. So we're going to have to divide by 3 when we do this. So we can write this as 1/3 ln of 3x minus 4 plus c. So we've seen on that last page that we can divide by the tail of the inner function if the inner function is linear. What if the inner function is not linear? Let's take something that's really close to linear, like x squared, and the antiderivative of e to the x squared. Is this going to be, using the logic of those last few problems, e to the x squared divided by the derivative of x squared, 2x, plus c? Well, let's find out. To figure out if this is actually correct, we just need to take its derivative and see if we get back to e to the x squared. So pause the video and take a minute to do that. All right, so when we take this derivative, the plus c is going to go away. That's just 0 when you differentiate it. But we have to do a product, or a quotient rule rather, for the rest of this. So using my box and ribbon, I've got e to the x squared, 2x, and their derivatives. This is going to be e to the x squared times a tail of 2x. Up here we've just got 2. Doing the ribbon now, multiplying these two together, this is going to be 4x squared times e to the x squared. And then going the other way, we're going to have minus 2e to the x squared. All over this thing squared, so that's going to be 4x squared. Now I need to try simplifying this to see if it ends up being e to the x squared. All I can really do to simplify this is factor out an e to the x squared, which would leave me with 4x squared minus 2. 4x squared minus 2 is not going to cancel out just plain old 4x squared. So I cannot simplify this to get e to the x squared. Those two are not equivalent. So based off of what we've done here, it looks like that dividing by the derivative is only going to work if the inner function is linear. It's not going to work in any other situation as far as we know. So that's it for this one. Until next time, this is Mr. Sutton signing off.